Hello, my name is Amit Paz. I'm from the University of Vienna, and this is a joint work with my colleagues Pierre Fréniaud from IRIF in France, and François Lagarde and Harumichi Nishimura in Nagoya University in Japan. And this is a brief announcement about distributed quantum proofs for replicated data. So in the replicated data problem, we have a network system where some of the units, called terminals, have data in them, and they should all contain replica of the same data. And I want to make sure that this is indeed the case, that if all the replica are the same, then everybody is happy. If not, someone sees that there is a problem. So these kind of problems of certifying that a network with labels or data on it has some desired properties was studied a lot in distributed computing under many different settings and many different names. And we give the quantum take on the quantum setting for these kind of problems, which we call distributed quantum Merlin-Arthur proofs. And why? So we extend to the quantum setting the Merlin-Arthur protocol, distributed Merlin-Arthur protocol that was presented 2 years ago in Potsdam. We have many players in this setting. One is Merlin that sees the whole network, and the other is the verifiers that are called Arthurs, and they act in two phases. The first, the Merlin phase, Merlin assigns certificates to the units. And Merlin sees the whole network, gives these certificates once, and then goes away. And then the Arthurs, the units of the network, have to manage themselves, exchange messages, each one with its neighbors, to verify that the state is indeed as expected. In our case, to verify that the replica of the data are all the same. And if we think of real networks, we think of one time of hard computation of the certificates or getting certificates from the cloud. And then you want the network to act by itself, certify every once in a while that the state of the system is still okay, and repeatedly do this until something goes wrong, and then maybe you have to recompute the certificates. So one way to do this, the simplest way to certify that this copied data is the same in a network, is to use as certificate a whole copy of the data, a copy of the full data. This is, of course, very inefficient, but it works. Why it works? Every terminal will make sure that his data equals to his certificate, and then the units exchange messages with the neighbors, exchange the certificates in this example, and make sure that all the certificates are the same between one unit and its neighbors. Now, if this is not the case, then either one of the terminals will say, my certificate is not the same as my data, something goes wrong, we have to recompute, or maybe all the terminals are fine, but then the certificates have to be wrong at some place, and then two neighbors will see that their certificates are not the same, and again, say something is wrong, we have to recompute or to reduplicate the data and so on. So the goal is to have a mechanism that if all the replicas are identical, that all the nodes accept, are happy, and can reuse the certificates. And if they're not identical, then someone rejects. It doesn't have to be the same one that has the wrong data, but one of the units of the system, at least, will have to raise an alarm saying something is wrong. The parameters of this problem, or the main ones that we look at, are first of all n, the size of the replicated data. We use n for this, as done in communication complexity, and not for the size of the network. We use t for the number of terminals storing data in the network, and r for the radius of the terminals, which is, roughly speaking, the largest distance between two terminals. Now, the goal is to minimize both the certificate and the message sizes. The way to do this in our work is to use quantum states or quantum bits, and both as certificates and as messages. This was, again, done before in distributed computing, but not in the not in the context of distributed certification. So our main results is first defining this mechanism of distributed quantum Merlin-Arthur proofs. Then we show that using this mechanism, you can have a certification mechanism where both the certificates and the messages have size that is only logarithmic in the size of the data. So if you think of the data as being very large, much more than the number of terminals or the distances between them, you get logarithmic size certificates. And finally, we show that you cannot do the same in the non-quantum setting. In the classical setting, even if you use randomization, either the certificates or messages have to have at least linear size. So how do we prove this main result? How do we prove that you have a protocol? What is the protocol or the mechanism that use only logarithmic size certificates and messages? This will be as following. I'll show you this only on the line for this talk. So we think of a line with two endpoints, Alice and Bob, having inputs X and Y, and want to make sure the inputs are the same. Now, this is a classical question in communication complexity if the line is of length one edge. That is, if Alice and Bob are neighbors, and you can solve it using randomization and no quantum states. Just Alice and Bob pick a random hash function, and then Alice hashes her input X using this function, send it to Bob. Bob hashes his own input Y and make sure that the message he got from Alice is the same as the hash of his input Y. And this can be done very efficiently, as I mentioned, if you have a very short line, if Alice and Bob are neighbors. But what happens if you have a longer line? This cannot be done because you want the nodes only to communicate with their neighbors. You don't want to flood the network with messages for this certification procedure. So you may think, okay, but this is not a very big problem because we can just use the hash of X as a certificate because that's anyway what you want to send from Alice to Bob. But unfortunately, this doesn't work because you cannot choose a random hash function and then have certificates, not in our setting at least. And you cannot let the prover to choose a hash function because maybe a malicious prover will choose a hash function that hashes the same X and Y, even if they are not the same. And then everything will look okay, but it's not really okay. Actually, we know that, I'll just comment that we know that you cannot have these small certificates and small messages as will happen in this case because we also have a lower bound. So what do? We use quantum states. In our case, we define what is called quantum fingerprints. So for a string X, we can have a fingerprint, h of X, which is a superposition of many hash functions and the hashes of X under these functions normalized. And if you have these quantum fingerprints, you can verify, as certificates, you can verify the state of the system by having Alice and Bob and all the terminals checking. So Alice will check that the fingerprint of her input X equals to the certificate she got. Bob will check the same for his input Y and the certificate he got. And all the units, any two neighboring units, will make sure that their certificates, their fingerprints they got as certificates, are the same. So this looks very simple actually, but it's not. And why? There are many challenges. I'll mention a few now. One is just checking equality between quantum states. It's not totally trivial, but there is a test for it that I'll mention more about later. But harder challenges has to do with the fact that you cannot clone quantum states. So if your certificate, let's say you're node V in this figure, your certificate is some fingerprint, you send it to B, you send it to your right, and you receive a certificate from your left. Now you want to check that your certificate and the certificate you got are the same, but you don't have a copy of your certificate anymore because you send it to Bob, and you cannot keep a copy and send a quantum state. And similar problems occur when you want to reuse the states for verification. If you send the state, you don't have it anymore for verifying the state of the system again and again. And a similar problem is that you cannot reuse the quantum state you got for verification if the equality test may corrupt your state, your quantum state. And this can happen in some tests of quantum states. And finally, another problem is that the equality test that we know and use in quantum computation it's not clear what happened with this state when you have a corrupted state that is, so we said, are certificate is a quantum state that is superposition of several states. It's a product state. What happens if the prover gives you a state that is not even a product state? Would the equality test still work? So we had to overcome these and others. The base is, first of all, choosing the right family of hash functions for this quantum fingerprint. And this family of hash functions have the property that if x and y are equal, then the inner product of the fingerprints is 1. If they're not equal, then the inner product is very small, it's almost 0. And then we use a classical quantum or widely used quantum test, which is called a swap test for testing equality. In this test, we accept with probability half plus the inner product squared over 2, or more concretely, probability 1 if x and y are equal, and probability only half plus epsilon if they are non-equal. And we analyze this swap test a bit more to make sure that the quantum states do not collapse if x and y are equal. So as long as the system is okay and the certificates are okay, you can reuse the certificates. And the swap test can also handle non-product states that, as we can have here. In the wrong case, the states can be non-product states, but they will still be okay with the swap test. They will not pass it, but the swap test will catch them. Other challenges we had to overcome is handling general graphs and not just a line, handling graphs with more terminals, systems with more terminals, and proving lower bound, the lower bound that I mentioned before, for the classical distributed Merlin-Arthur proofs for this problem in the non-quantum setting. Sorry. So just to conclude, we show that quantum states and using quantum bits give exponential advantage for distributed certification. And open problems are, first of all, to have other quantum distributed quantum Merlin-Arthur protocols to certify in other Boolean predicates on labeled graphs, say that the graph or network doesn't have triangles or that it is symmetric in some sense. And another problem is to prove lower bounds for this quantum distributed certification mechanism. And I will stop here. Thank you very much.